This screencast is going to be an extension of the previous one on multiplication rule. This is a screencast on the total probability rule. So let's first review the multiplication rule. If we have two intersecting events, we can write different expressions for the probabilities of A with B based upon their individual conditional probabilities and the probabilities of A and B. So we're going to use this. We're going to kind of take a twist on the multiplication rule in order to create the total probability rule. The total probability rule assumes a couple of things. First, it assumes that you have two events that make up the entire set. So in other words, here, the entire sample set is a combination of A and its complement. It also assumes that A and A complement are exhaustive. So what this means is that those two sets, A and A prime, are exhaustive, what we call exhaustive. They make up the entire sample space. We're also assuming that there is no intersection of A and A prime, and so that means these are mutually exclusive. So we assume mutual exclusivity between those two events, A and A not. And then we also have another event in here, a subset. We have B. Event B represents this entire shaded region. But we have two parts of B. B can either come from the top half here. So we have this region, and that's known as the intersection of A and B. And we also have this lower half of B, which is the complement of A and its intersection with B. So if you look at this, the probability of B is going to be composed of two parts. It's going to be composed of the intersection of A part and the intersection of the complement of A. So we can rewrite this probability of B as the following. So that's what we get. We get the probability of B in this case comes from two different contributions. Now it's important to remember the multiplication rule that I just showed a few moments ago. We can substitute in for these two different contributions, these intersections here. We can rewrite this in terms of conditional probabilities. And we get the following. We get the probability of B is the conditional probability of B given A times the probability of A plus the probability of B given A not has occurred, so the complement of A times the probability of A prime. And this here is known as the total probability rule. Let's go through an example, and I can kind of explain where or why you might want to use this. So the total probability rule is given by this expression. A tennis player wins 60% of her matches when she scores the first point of the first game. She wins only 10% of the matches when her opponent scores the first point. If she scores the first point 30% of the time, what fraction of matches does she win? Now, in any probability problem like this, it's always nice to write down or define what your different events are. So I'm just going to say SF means she scores the first point. And our second event, if you look in the problem statement, we have problems related to winning. So I'm going to say W means she wins the match. Now let's just kind of look at the problem statement here. We are already given a couple of items of information. This first sentence, a tennis player wins 60% of her matches when she scores the first point. That's a conditional statement. So the probability that she wins given or if she scores the first point, that's a conditional statement, and we know that that's 60%. So a lot of times it's just looking at the problem statement and kind of determining if we have a conditional probability, if we have a probability, and so on. We are also given indirectly the probability that she wins given that she doesn't score the first point. So she wins only 10% of the matches when her opponent scores the first point. That would be SF prime is equal to 10%. And now we have to kind of see what we're asked for. We're being asked if she scores the first point 30% of the time. That means we're given the probability that she scores first. So we're saying if that's 30%, then what we're trying to find is what fraction of matches does she win? So what is the probability that she wins? Now, you usually want to take the data that you know and you want to kind of see which of these probability rules relates to that or relates the variables that you have to what is unknown. And you can see here that we can rewrite the total probability here in terms of the following. So we can rewrite this as the following here. So let me put a question mark. We're trying to find the probability that she wins. Let's put a check mark next to everything we know. So we know that. We know the probability that she scores first is 30%. The probability that she wins if she doesn't score first. We don't know directly what the probability of SF prime is, but because she either scores first or she doesn't score first, this is just 1 minus the probability that she scores first, and that's just 0.70. And so if you plug all these numbers in, you end up with the probability that she wins is equal to 25%. And so that's an example of how we might use the total probability rule to solve an actual problem. By the way, this can be extended to if you have more than two events. So here we have E1 through E4. Those are exhaustive sets, meaning they add up to the total sample space. They're mutually exclusive, meaning there's no overlap between events 1 through 4. But now we might have a event B that is shared among all 4 of those other events. And we want to write this in terms of total probability rule. Doing something similar as we did earlier, we can redefine this using the intersections multiplication rule. We can define it as the following. Instead of 4, I've put in a k. So it's just the individual probabilities of each event multiplied by their conditional probabilities, and we sum those. We can just write the summation symbol there, where we're summing all the probabilities, the conditional probabilities of B given EI, and we're multiplying by those individual probabilities of E of I. Hopefully this screencast gives you a better idea of how we can use the total probability rule to solve problems.